An important aspect of Lewis dot structures are resonance structures. Resonance structures are simply different forms of a molecule where the chemical connectivity is the same, but the electrons are distributed around the structure differently. An example is ozone. So ozone is O3, and this is the Lewis dot structure for ozone, and it has two different resonance structures. And the reason why we need resonance structures is because Lewis dot structures are a little bit limited, because they show us bonds as if they were localized. Neither Lewis structure is correct because electrons are actually delocalized over this entire molecule. And we're going to talk about what that means. Lewis structures depict electrons as localized, either on an individual atom, lone pairs, or between two atoms, a shared pair. Actual structures for molecules, electrons are actually delocalized. And so this is a limitation of Lewis. Actual structures are an average of equally valid resonance structures. So really you have that double bond, those electrons that form the double bond are shared between all three of these atoms in ozone. So we give this dotted line to show the delocalization of electrons. And once we start talking about valence bond theory and molecular orbital theory, it'll make a little bit more sense what orbitals are allowing for this shared electrons over this entire molecule. So because we have delocalization of electrons, for ozone, we don't have a bond order of 2 here, so we don't have a double bond here and a single bond here. What we actually have is we have a bond order of 1.5 over this entire molecule. So bond order is just a measure of the strength of the bond. We typically call a double bond a bond order of 2, a single bond a bond order of 1, a triple bond a bond order of 3. And we can measure strengths of bonds using a variety of techniques such as infrared spectroscopy. And the stronger this bond, this will affect the vibrational frequencies. And so we can interpret from spectroscopy that ozone doesn't have a single bond, it doesn't have just a double bond and a single bond, but it actually has a bond order somewhere in between a single and double bond, around 1.5 for ozone. So let's do an example problem. Write resonance structures for the nitrate ion NO3- and find the bond order.
Write the resonance structures for the nitrate ion NO3-. What is the bond order for the NO bond? Okay, so we're going to start by drawing our Lewis dot structure, and hopefully you guys have gotten a little bit of practice drawing Lewis dot structures, but briefly, we count the number of valence electrons. And remember previously, if you look at the periodic table, nitrogen has 5 valence electrons, and oxygen has 6 valence electrons. So our total number of valence electrons is 5 valence electrons from the nitrogen, 6 for each oxygen, so 3 times 6, plus 1 for the negative charge, which is a total of 24 electrons. So again, we put the least electronegative atom in the center and connect it to all of the other atoms. Alright, and now we can see that our nitrogen doesn't have a full octet, so we're going to put one of these lone pairs from an oxygen to form the octet for nitrogen. So we get a structure that looks like this. And if you were to go ahead and calculate the formal charge, we have +1 on the nitrogen, 0 on this oxygen, and -1 on each one of these oxygens. So overall, the charge on this structure is -1. So this is an example of one of the resonance structures for nitrate. The problem is that we can draw 3 equivalent resonance structures of nitrate because we can have the double bond between this oxygen, or this oxygen. So let me just show you what if we were to draw all 3 resonance structures. So it's really important to note that the nitrate ion is not changing back and forth rapidly between these two structures, but rather the actual nitrate ion is an average of these three representations. This is because the electrons are delocalized. What we actually have is that this double bond is actually spread out over the entire molecule. So we have 4 pairs of electrons spread out over 3 regions of electron density. So we actually have a bond order for the NO bond of 4/3.
Alright, so nitrate is a great example of resonance and how the actual structure is a combination of these 3 resonance structures, and the bond order is 1 1/3. So another really good example of how resonance structures and Lewis dot structures don't quite tell the full picture is benzene. So you can draw a lot of different resonance structure of benzene with these double bonds sort of moving around this ring. And so basically these double bonds, which we'll talk about soon, are bonds made up of p orbitals forming pi bonds. And so the actual picture for benzene is we have this delocalized pi bond over this entire molecule. It kind of looks like a hamburger bun. So I really want you to get to the point where you can think about bonding. It's not localized like these Lewis dot structures. We actually have this delocalization of electron density. Okay, so but Lewis dot structures are really useful. So we need to also talk about exceptions to the octet rule. So there are certain molecules that are electron deficient, and those are usually small molecules, especially beryllium and boron. These two often form electron deficient molecules that here boron doesn't have a full octet. It has only 6 electrons surrounding it, and here beryllium just has 4. There's also odd electron species. These are called free radicals. I study free radical chemistry quite a bit, and free radicals are not usually very stable. Some free radicals are more stable than others, but this is an example where you're not going to follow the octet rule simply because you have an odd number of electrons. The next example is expanded valence shells. So anything, you can have expanded valence shells for anything that's in period 3 or bigger. So phosphorus and sulfur are great examples where you're not following the octet rule. So here sulfur, the central sulfur atom, has a total of 12 electrons, and here this phosphorus has 10. So these are examples of an expanded octet or expanded valence. So I wanted to talk briefly about choosing the most important resonance form, which one's probably most similar to the actual bonding picture. So we kind of touched on this briefly, but you want smaller formal charges. You really prefer to have no formal charge on any atom for a resonance structure. If you have to have formal charge, you want smaller formal charges are preferable to larger ones. So it's better to have -1 or +1 rather than -2 +2. And you typically don't want 2 negative formal charges right next to one another. And negative formal charges should reside on more electronegative atoms. All right, so here's an example of a molecule that has 3 different resonance forms. And remember that we want to minimize formal charge. So this one automatically is not going to be the best resonance form because we have a -2 formal charge. So we want smaller formal charges if possible. So the best resonance structure is going to be this resonance structure number 3 because it has the negative charge is on the oxygen rather than the carbon or nitrogen. So again, we're probably going to have some of these contribute to what the actual bonding picture looks like, because remember that we don't have these localized bonds, we have these delocalized bonds. So the actual bonding picture is an average of these 3 resonance structures, but it's going to be heavily weighted towards this resonance structure.